Welcome to our video on regression analysis. In this lesson, we'll explore what regression analysis is, how it works, and go through a detailed example. Regression analysis is a statistical method used to model the relationship between variables. In simple linear regression, we model the relationship between a single explanatory variable x and a response variable y. The simple linear regression equation is y approximately equals beta 0 plus beta 1 times x, where beta 0 is the intercept and beta 1 is the slope. These parameters are chosen to best fit the data by minimizing the sum of squared distances between the observed y values and the predicted values. The least squares method gives us formulas to estimate the slope and intercept. For the slope beta 1, we divide the sum of products of deviations of x and y from their means by the sum of squared deviations of x from its mean. For the intercept beta 0, we use the formula beta 0 equals y bar minus beta 1 times x bar. To evaluate how well our model fits the data, we use several measures. These include the total sum of squares, or SST, which measures total variability in y, the regression sum of squares, or SSR, which measures variability explained by the model, and the error sum of squares, or SSE, which measures unexplained variability. These satisfy the relation SST equals SSR plus SSE. Finally, the coefficient of determination, R squared, equals SSR divided by SST, representing the proportion of variance in y explained by x. Now, let's work through a detailed example of simple linear regression. We'll use a small data set with 5 data points. First, we calculate the mean values of x and y. The mean of x bar, is 3. The mean of y bar, is 5.6. Next, we need to calculate the sum of products of deviations and the sum of squared deviations of x. We find that the sum of products of deviations equals 22, and the sum of squared deviations of x equals 10. Now we can calculate the slope and intercept. The slope b1 equals 22 divided by 10, which equals 2.2. The intercept b0 equals y bar minus b1 times x bar, which is 5.6 minus 2.2 times 3, giving us negative 1.0. So our fitted regression line is y hat equals negative 1.0 plus 2.2 times x. Using our regression equation, we can calculate predicted values and residuals. For each x value, we compute y hat using our equation, then calculate the residual as the difference between the observed y and predicted y hat. Next, we assess how well our model fits the data. The total sum of squares, SST, is 51.2. The error sum of squares, SSE, is the sum of squared residuals, which equals 2.80. The regression sum of squares, SSR, equals SST minus SSE, which is 51.2 minus 2.8, giving us 48.4. Finally, R squared equals SSR divided by SST, which is 48.4 divided by 51.2, approximately 0.945, or 94.5%. Finally, let's interpret our results. The slope of 2.2 means that for each 1 unit increase in x, we predict an average increase of 2.2 units in y. The intercept of negative 1.0 represents the predicted value of y when x equals 0, though this may not always be meaningful in practice. Our R squared value of 0.945 indicates that about 94.5% of the variability in y is explained by our linear model with x. Let's visualize our final regression model. Here we have our original data points in blue and our fitted regression line in red. The green vertical lines represent the residuals, the differences between observed and predicted values. As you can see, our line fits the data quite well, which is consistent with our R squared value of 0.945. In conclusion, regression analysis is a powerful statistical tool for modeling relationships between variables. We've learned about simple linear regression, including how to estimate parameters using the least squares method, assess goodness of fit with R squared, and interpret the results. This technique has countless applications in fields like economics, psychology, engineering, and data science, helping us understand relationships, make predictions, and inform decision-making.